Hello and welcome to the first ever Unreal Engine with a group. Thank you. You know, this place means something to me. 18 years ago, I made the first public Sumatra demo here. Anyone remembers that? We had a great time. And you know, I was excited, but it's nothing like the excitement I have today showing what we have to show you. So, my name is Marc Petit. I run the enterprise business at Epic Games. And my team is a team of engineers, pipeline specialists, technical artists, and we are dedicated to helping you implement Unreal Engine in your production pipeline, whether you work in film, television, broadcast graphics, architecture, automotive, retail, everything, even artificial intelligence, you will see today. Tonight, we put together a great lineup of presentations for you. It's going to be entertaining, you're going to learn a lot of things. First, Tim Sweeney, our CEO and founder, will come and give you a little bit of an update on Epic Games and Unreal Engine. Then we've selected for you two forward-looking presentations. One is going to be about interactive visual humans, and the other one is going to be how you can use a game engine to train intelligent agents, and particularly autonomous vehicles. Then we'll have a more pragmatic section to the event. We'll talk about workflow. Workflow is a big problem, getting data into the engine, being productive. We'll talk about that. We have some good news and some new software for you. And finally, we'll present to you 3 case studies, which we think will represent for you what is the current state of real-time production. But now let's get going. Tim Sweeney does not need introduction. So let me welcome on stage our founder and CEO, Tim Sweeney.
Thank you. Thanks a lot, and thank all of you for coming. It's a real honor to have so many computer graphics industry luminaries here in this room. Now, Epic has a long history with SIGGRAPH. 2 years ago, we were here at Real Time Live with our short film, A Boy and His Kite. Now, this was a real first effort to show that it's now possible to build very high quality, cinematic quality animated content in real time using the Unreal Engine. And then last year, we returned to Real Time Live in partnership with Ninja Theory to show some real-time motion capture technology in Hellblade. And then we used that real-time motion capture system to build a short film on stage live, going from pre-visualization to final with a small scene in 5 minutes. And these efforts were well received. Over the past 2 years, the Unreal Engine has sparked a real revolution in real-time cinematography. And this is not just in previs, that's been going on using game technology for about a decade now. But today, top studios are producing movies and television with final pixels that are output in real time from the Unreal Engine. And only the Unreal Engine produces these final quality pixels in real time at the quality level that's demanded by Lucasfilm, ILM, General Motors, and other leading companies. This was demonstrated in the film Rogue One, where several shots of the droid K2SO were actually rendered in real time and slipped into the movie as a proof of the concept being possible. I think this is just the very, very beginning of the widespread adoption of this technology across other media. So in the middle of this real-time revolution, I'm really honored to talk to all of you at the opening of Epic's first SIGGRAPH user group meeting here and tell you about the state of Unreal. And the state of Unreal is strong. Since we made Unreal Engine 4 widely available to everybody 2.5 years ago, over 3.5 million users have joined Unreal. Developers building games, film, television, architecture, and any number of enterprise applications. We have a world-class team of engineers and tech artists at Epic building features for leading-edge applications and helping customers like you to succeed. The range of these applications, 10 years ago, it was all about games, but the range now is really astonishing. Who would have thought that some technology that was birthed in building real-time games would now be used to support development of next-generation human-machine interfaces in cars, or would train AIs for autonomous applications, or aid in drug discovery? We really didn't see these things coming until the last 2 years as these users started contacting us and telling all the crazy things we were doing. But now that it is happening, we're on it. Our business is growing rapidly, and we're here to help our customers to succeed. And we also need your help. we're a very rapidly growing team, and if you'd like to join Epic and help to create the future together, working on leading edge engineering stuff, artistry, design work, or play any sort of supporting role, please visit epicgames.com and get in touch. Now I'd like to talk a little bit about games. Last week we released Fortnite, our new multiplayer action building game. By day you scavenge resources and you build forts, and then night monsters come out and you defend them in a very cooperative, fun, highly stylized visual environment. The reception to this game has been amazing, with 500,000 pre-orders at launch, and Fortnite is now on track to become Epic's biggest success ever. And that's saying a lot. This is the company that has its heritage in games like Gears of War and Unreal Tournament, and this game that we are both developing and publishing ourselves is on track to be the biggest, unless it's beaten out by Paragon, which is Epic's new MOBA. The Paragon brings AAA production values to an action MOBA that runs at 60 frames a second. The Paragon's first esports competition is beginning this weekend. And this is a game where it really strives to bring realistic graphics, high-quality photorealistic graphics and visual humans to a gaming genre that was previously defined by relatively low-fidelity, overhead view mechanics. But this experience with both Paragon and Fortnite kind of highlights the soul of Epic, and that is that we make games with our engine, and we use our games to push our technology forward. Paragon is pushing on real-time rendering performance, it's pushing on visual humans, Fortnite is pushing on visual cinematography, and many other areas of the technology, but it's this synergistic development of games and engine together that enable us to make such a polished piece of software. And you can count on every time you experience a bug in Unreal Engine yourself, we've experienced it 10 times and are just as motivated to have it fixed as you are. The other really interesting thing happening now is that teams of all sizes are using the Unreal Engine to build great games, from AAA blockbusters built by teams with hundreds of people on them, to award-winning indie titles. Now, this is Astroneer. This is a game that was built by 6 people originally at System Era Software, but it launched and hit #1 on Steam really quickly and was a huge financial success. Unreal Engine is also leading a revolution in high-end mobile gaming. Now, this isn't a surprise because today's smartphones has as much performance as the consoles of the previous generation. And that's a gigantic change in the mobile industry. So some of the interesting successes we're seeing now include Netmarable's Lineage 2 Revolution. Now, this is a leading-edge action MMO where you can have more than 100 players on screen visible all at once, running on a smartphone. And this is one of the biggest mobile launches in history, earning $176 million in its first month of launch. PlayerUnknown's Battleground is another amazing record setter, and this game kind of came out of nowhere, but introduced some really innovative game mechanics, and in its first couple of months it sold more than 4 million copies on Steam, earning over $100 million in revenue. And it's not alone. Last week the top 3 titles on Steam were all made in Unreal. I think what we're seeing here is that following the last decade's giant growth in indie development, we're seeing a fight to quality, with the best developers, filmmakers, and other industry leaders recognizing the importance of powerful real-time graphics, highly productive tools, forged in the trenches of game development, and a track record of commercial success. And so we really offer a sincere thanks and congratulations to all of our partners who made this possible by blazing the path towards this new real-time future. To launch Fortnite and to hone our animation tools, we built a 3-minute cinematic trailer for Fortnite that you'll see later in this presentation. Unreal Engine's sequencer tool unleashes artists and designers' creativity by streamlining the filmmaking process. It's a completely real-time cinematic editing tool, so you can work live, you can iterate really quickly, and you can ship back a piece of work. The content is completely portable. You can build a game and then have cinematic assets for free that you can use to produce all of the marketing materials for your game, or VR apps, or AR, or anything else that runs in real time or offline. In fact, this is the first year that SIGGRAPH is accepting real-time content in the SIGGRAPH Computer Animation Festival. Two real-time shorts have been selected for this festival, and both are powered by the Unreal Engine. So other folks will tell you more about these projects tonight. And then partners across the entire industry are achieving amazing things using the Unreal Engine. Zafari is a beautiful animated TV series that's being produced by Digital Dimension in Montreal in real time. You'll hear more from them later. Disney is blending storytelling and gameplay to create a really interesting new interactive show that engages the viewer with Amigo to the rescue. And this was just nominated for an Emmy. It's amazing to see all these crazy things come together in real time that were previously done, using multiple hours per frame of rendering time. And now General Motors chose the Unreal Engine to create a real-time car commercial in partnership with the mill. So you start in a car configurator, you can pick out what color of car you want, what model, and all the materials in the car, and then you can see a real-time car commercial featuring your car that all runs live. This will be presented at this SIGGRAPH in real-time live, so we hope you get a chance to stop by and see it. On the VR front, we released Robo Recall for free on Oculus Touch. This is a really cool fast action game with immersive motion controls. You're actually reaching out and grabbing robots and throwing them and picking up weapons and shooting and doing all these crazy things. But we not only released the game for free, we also released the full content base and source code for everybody to learn and experiment with. And this highlights the real open philosophy that Epic has developed with Unreal Engine 4. Anyone can go to unrealengine.com. You can download our complete engine for free, and you can get started learning or building projects at a commercial scale and get started. And our complete C++ source code, not some part of it, but the entire engine and everything that we use internally to develop our own games is available online on GitHub for free also. And so this is our spirit. We give you absolutely everything we have ourselves as game developers so that you have every advantage we have when you go about building your content. Also in VR, at Disney's D23 event, they unveiled Marvel's Powers United VR, built with the Unreal Engine 4 technology. Also, Blade Runner 2049, Replicant Pursuit, made headlines at Comic-Con last week, another VR experience. And then Spider-Man Homecoming is the game built to support the next big film in the franchise. And this highlights that top studios are moving to real time and choosing Unreal for its high quality production values because they want to create experiences, whether games or any other form of entertainment, that really show they're off their intellectual property in the highest quality light. And then we've been working very closely with Apple lately. At the Worldwide Developers Conference, we were on stage with them when Apple announced support for VR on Mac. Now, ILM and Epic worked together on stage to demonstrate a scene from the Star Wars universe. But it wasn't only that. We also showed the Unreal Editor running in real time on Mac in VR. And this highlights, we think that VR is not only a medium for content consumers, but it's also going to be a revolutionary media for content creators. What more form of productive and natural content creation can you imagine than being able to reach out and grab objects and move them around with your hands and sculpt them with full 3D 6 degrees of freedom using these motion controllers? We think this is going to really revolutionize the industry over the next few years, and our pioneering works with the Unreal Editor have done a lot in this area. Our spirit has been, from the very beginning, we don't create some little tools that run in VR. We made the entire Unreal Editor, the entire tool set, and the entire user interface available in VR. So that when you're in VR mode, you can pick up the menus and do absolutely anything as you go about building your content. At WWDC, Apple also announced ARKit for iOS, bringing AR to hundreds of millions of users. This was really big because it happened years before anybody expected AR to go mainstream. Now, to demonstrate Apple's amazing new software, we helped Peter Jackson's AR startup, Wingnut, demonstrate an amazing tabletop science fiction experience here in real time. We really believe that AR is going to change the world. The seamless integration of computer graphics into the real world will revolutionize gaming and hundreds of other fields. For the folks in this room, just imagine the possibilities for television and for virtual production when you can look through a camera viewfinder and see your final scene, both the real world actors and the CG composited in together live in real time. And these devices, their smartphones and tablets they're running this are just the very beginning. We work with Magic Leap and other partners who create the next generation of technology that will run on entirely new display form factors. Now finally, across film, games, VR, and AR, great stories require great characters. So digital humans technology has been a really high priority for Epic to develop from the very beginning. And so, to redefine the state of the art, Epic and Tencent have partnered together with Mike Seymour, with Trilateral, and with Cubic to carry out an experiment that we think is really going to be interesting for the folks in this room. And to introduce this project, I'd like to hear a few words from Mike Seymour up on the screen. Mike?
Thank you. This is our Digital Human project, which is a collaboration of a whole lot of companies: Epic Games, Trilateral, Twinmotion, Tencent, the Wiki Human team, Sydney Uni, FX Guide, a whole bunch of people coming together to produce, well, a virtual human, and not only a virtual human, but one rendered in real time, puppeteered or driven in real time, rendered in real time, and not only that, but at 90 frames a second, in stereo, in VR.
That obviously wasn't me, it's digital me, virtual Mike. So I really honoured to be here to go through what we've been kind of doing with the Meet Mike process. And I thought we'd actually kind of quickly run through how we put that together. Now this is a research project and it's a collaborative effort, as we've heard from Virtual Meet, of a whole lot of people coming together to put this together. So let's have a look at how we kind of did it. It started out with us doing a very detailed scan of my head at USC ICT in the light stage, which was pioneered by Paul DeBevick and his team. And we put that together with obviously multiple cameras taking photographs of my face and producing, of course, sort of a photogrammetry reconstruction, but not just of a still, of course, but being all kind of weird expressions, because this produces a bunch of facts or facial sort of action units that allows us to then produce any other expression that I might want to come up with. And at the moment that we did this, which was a little like last year, we, for a second, I had the most scanned face in human history, but I'm sure somebody else owns that honor now, but for a brief second I had it. And that let us put together this head and of course move from what is essentially a point cloud to something that has cohesion and is consistent over time. So we get the basic model out of that, we can then apply to that the various textures that we got. This is kind of roadkill, Mike. And of course we can get these 16K textures and then use them to produce really high quality work. Now at this point this is looking pretty good, and we thought we'd sort of put it up side by side with my head, and as you can see one of them is pretty good and the other one, well, has kind of weird eyes, right? At this point this is all work being done inside a group called the Wiki Human, and I totally suggest you guys check it out because it's this research effort, which I'll come back to at the end, which is all about education and giving back to the community. Anyway, we need some eyes, right? So we went to our friends at Disney Research Zurich and got my eye scanned. If you've ever seen Clockwork Orange, you get the idea. But this is also research that these guys have been doing that's since moved on, and this actually feeds into pipelines in the Disney franchise, obviously, companies like ILM and stuff. So we've got the eyes now. We now have a rig, and we went to Trilateral in Serbia, who produced some of the world's best facial rigs. And this allows us, of course, to now move the face based on those facts settings. So, at this point, we went to some meetings and basically talked to everybody and saw if we maybe couldn't do this in real time. And this is when we came to the Unreal 4 and the Unreal Engine 4. Here at Epic, we managed to get all of this data into a real-time system, and the guys even gave me some hair, which is pretty cool, right? Actually, about 75% of the 440,000 triangles used to put this together actually got into my hair, so we're kind of glad that I'm receding a little bit because it saved a bit of GPU time for the rest of my face. Okay, so actually there was a lot of stuff over how bald I should be. Okay, so we got it working, we got the light working. Now, of course, we want this thing to come to life. And we had this plan inside Wiki Human for the Make Mic Move. So that's what we did next. We tried to see if we could place that mic in an environment and then make that happen. And to show you that this was kind of coming together in a second, I'm going to go over to Michael and we're going to show you this happening in real time. But that was done by Technoprops, sort of lineage from the original stuff with Avatar, stereo rig, and you can see this because we're running this up at the main show floor. So that gets solved with some deep learning algorithms so that it's a markerless system. We can not just reconstruct my face, but actually work out what those fax expressions are that relate to the original scan. Of course, we have to do this in real time. And this is like a real killer problem, right? Because we don't have much time. You might have 2.5 hours maybe in a feature film to render a high resolution final frame, right? 2.5 hours a frame. We're doing it up at the show at 90 frames a second in stereo, in VR. So to render this stuff in real time is just an astonishing feat, but the guys managed to do it with a cascading set of PCs that are all running sort of top of the line 32 gig, like 10 core, high-end NVIDIA cards, and we got it to run. And so this is actually a render in real time, but not animating in real time. What you saw when I just came on stage was, of course, the real-time render. So if we can now go over to Michael, just to show that this is all rendering in real time. Okay, so Michael can now jump around while this is playing. Can you give me the X-Men version where I look really cool like Storm? Okay. I should take that off actually. Disney did a lot of work to give me some eyes, we shouldn't screw it up. So all of this is rendering in real time, obviously here tonight, but as I said, up at the show, it's rendering in VR, so we welcome you guys to come back. We're on every day around 10:30 to 12:30 doing interviews, and in fact I made Tim suffer an interview today, he was terrific. With that, if we can just go back to my slides, 1 second. I just want to, again, iterate, this is a project that's a collaboration of everybody that's been working, and so this material has been given out as part of WikiHuman, which kind of falls in line with Tim's point earlier about being free and giving back to the community. Here are all the companies that have contributed. I've just been a small cog in the wheel, and with that I'll say thank you. See you guys later.
Thank you, Maximo. Thank you, Tim Sweeney. I want to call out this group of people. They're really great. They're doing amazing things in terms of bringing us high-quality digital humans in real time. It's really fun to see. So our next presenter is coming down from Silicon Valley. He's one of those guys with a big personality, big ideas, big entrepreneur with a big vision. And I'll let him explain his vision. He is simulating and bringing autonomous vehicle to the world by scanning San Francisco in real time. Please welcome Tim Cantley-Clay from Zoox.
Good evening. So my name is Tim Cantley-Clay. I'm the CEO and co-founder of Zoox. Zoox is a stealth mode, Silicon Valley-based robotics startup. We're 270 strong, and our ambition is not to create a so-called self-driving car. Our ambition at Zoox is actually to make the most advanced autonomous mobility experience the world has ever seen. To enable that, we're going to need next generation simulation. And at Zoox we've been using Unreal Engine to build our simulation pipeline, and it's my pleasure to give you guys a sneak peek at some of the work that the team has been doing. So while we're building our own vehicle in parallel, we use other people's vehicles to test our stack. So here you can see a Toyota Highlander. It's got our sensors on it, it's got our compute in the back, and we've hacked into the VCU, the vehicle control unit on the vehicle, in true Silicon Valley style, and taken parasitic control of the vehicle. So this is actually San Francisco. And this vehicle, when it drives through the environment once, is fully calibrated down to around 3 centimeters. That's important because from that vehicle driving down the road to looking at this image here, that was a fully automated pipeline. So we've been able to reconstruct with the sensors very geometrically accurately the city environment. Then we can rebuild that using that mesh as ground truth into a much more efficient mesh, okay? And then of course, once we've done that, we're able to add dynamic agents into the environment. And that's important because what we're doing here is not just having a vehicle follow a Bezier curve around an environment. We're actually running full stack simulation virtually. So we're using synthetic sensors, and we're actually publishing them to another computer that's running the AI stack, and that's publishing it back to this computer that's running the simulation environment. And it's very important to us that this environment is geometrically accurate. We could use a synthetic procedural world, but what we actually want to do is test and validate how our AI works in a real city, so we can actually quantify over time the delta between our simulator's performance and the real world performance, which is obviously important for being able to trust your simulator. So here, let's have a look under the hood. So this is an abstraction layer that's simulating radar. So we use physically based shaders in Unreal. We've extended that with our own C++ code. And so again, over time, we're able to tune how the radar returns work virtually in simulation and how they work in the real world. So this is really important work for us to understand how the radar's operating in the environment. We can also simulate LiDAR, right? So that's emitting photons of light, hitting a surface and coming back and catching it. We use ray tracing to do that, which we're doing here. And then we actually publish the exact returns from this simulation in the exact packet format, how the actual sensor would publish it over TCP/IP to another computer that runs the AI stack. So it actually doesn't know if it's getting data from the real world or from the simulator. But then who does? And then we can also start training convolutional neural networks. So this is some research work we're doing at Zoox. Often when you want to train a net, you have to have what's called ground truth. You pay people to sit there and draw boxes over every pixel from the video feed and say this is that and this is that. Very labor intensive. Obviously in the simulator, we know what every pixel is. And so here we're saying, hey, green is road, yellow is sidewalk, red is car, blue is pedestrian, and training the net and seeing if we can transfer that AI from the simulator over to the real world, which we can do is a bit of a breakthrough. And then finally here, we show you the Zoox road network. So when we drive through this network, geometrically accurate, we've created vector splines that describe where the lanes are and what the rules of the road are. And we can also simulate the planner. Planning and autonomous driving actually happens just in an XY plane. It's a 2D construct. So when we change some code on the planner, we can run it through our high-performance computer called Hypercube, beautiful 10-rack GPU-based accelerator, and test with metrics that when we change the code on the planner, every single street in that city, we improve the efficacy of the system, which is really important. So what we're going to do now is jump out of the simulator world and go to some live action shots of our vehicle actually driving through San Francisco. We're learning where what's trained in the simulator is now working over real footage. Green being road, pink lanes, you guys get the image of what's happening there. This is state-of-the-art, super progressive work, and it's very important for us to understand semantically what's happening in the scene. This is another system we're using called DeepBox. We're running actually PR curves actually over 98% accuracy out to a 40-meter perimeter for recognizing cars. You can see in blue we have pedestrians, orange cyclists, and the little arrow on the top, we're also estimating with a neural net the pose state of the vehicle, which direction it's heading, which is really important for reasoning about how to move through the environment. Before we showed you the ZRN, the Zoox road network, here we're actually projecting that back into the camera on the vehicle, so we can actually test that we kind of got it right, and that the ZRN, the road network, actually lines up with what's happening in the environment. But we don't want to have to build this manually, so we're actually building some tools here. This is done last week. I thought I'd give you guys a look, where we're using a dense semantic segmentation net on the left, then we're analysing the lane in the centre, and then we're actually creating a polynomial, a vector line, off that lane in real time. So we actually want to get to the point where our vehicles can actually reconstruct the environment, not just in terms of the geometry, but also the rules in real time. And this is an amazing team, 8 people who have been working in the sim team at Zoox. Super young team, Zoox is hiring. If this looks interesting to you, I'll get the bar later and love to have a chat. Cheers.
I don't know about you, but the amount of data and the fidelity that you need to simulate those numbers vehicle, it's really mind-blowing. So thank you team, good luck with the project. Now I'm going to switch gear and we're going to talk about something new. We had a glimpse in the future, we're going to talk about something new, but something that's available today. I mentioned that my team is focused on workflow and pipeline, and that's something that's very near and dear to our heart, is to make sure we bring you solutions that allows you to use Unreal Engine extremely easily into any kind of pipeline. And to show that to you tonight, it's my pleasure to welcome on stage Chris Murray.
Thank you. Hello and welcome, everyone. Let's try that again. Hello and welcome. All right. My name is Chris Murray, and I'm the Technical Marketing Manager for Unreal Engine Enterprise. Thank you for taking the time to join us this evening. In this workflow section, we're going to be taking a look at 4 different things. We're going to be taking a look at AEC workflows, manufacturing workflows. We're going to be looking at an AEC application that was built on top of the Unreal Engine as its primary delivery vehicle. And we're going to be looking at large-scale data set workflows. So we have a lot to cover tonight. Many of us already know and realize the importance of real-time graphics and its transformative ability to transport us to different worlds and different places. But right now, we are witnessing a sea change of professional, high-end use of real-time graphics for non-games. And Epic is leading the way. So who is using the game engine for non-game applications? And it turns out it's a lot of you. A CG Architect rendering survey that was released about 9 months ago showed that Unreal Engine is the fourth most used renderer in various applications, specifically, obviously, design visualizations, but used as an offline render for generating images. And architects and visualizers realize that real-time interactivity is a better way to evaluate and communicate their designs. Milan architect Piero Lissoni at Lissoni Sociati in Milan, Italy, are really no strangers to beautiful designs. They've been designing environments, objects, furniture for a long time. How do they do it? Well, a clue comes to us from Piero Lissoni's quote that says, "I've kept the enthusiasm of a child. No matter how small or big and important a project is, it doesn't really matter much. I prefer to play every day." So at Epic, we know some things about playing. So how does Epic reconcile great design, technology, and the need to play every day with interactivity? We want to make it easier for you to iterate faster in the engine. We want you to be able to experience your designs in new and different ways. And for that reason, we'd like to introduce Datasmith. Datasmith is a workflow toolkit for getting all sorts of 3D data from numerous sources into the engine. Currently, in its current form, Datasmith is a 3ds Max exporter and importer and a separate CAD importer. The nice thing about it is we're kind of leaving asset anxiety behind. We have the ability now to export en masse geometry, lights, cameras, materials, textures. It supports V-Ray. It also supports Corona and Forest Pro. What's really great about it, besides those things that you just got there, obviously, is the fact that we're looking to save you hours of work. If you've imported things into the engine, you know that it can be somewhat arduous. You're bringing individual objects in as FBXs or group FBXs. It can be a little bit challenging to work with. So we want to save you hours and get you faster turns getting data into the engine. We want you to be able to ramp up quickly. No more tedious rework of materials, scene organization, and object placement. When I say ramp up, I'll show you what I mean by that in a minute. And we also want you to be able to experience it anywhere. And that's really one of the advantages of working with Unreal Engine, is that you can either go mobile, you can go AR, VR, the choice is yours. The bottom line is we want to have fidelity to the source of the content that you're creating as it comes into the engine. So let's go ahead and take a look at some things. I just want to show you a couple things over here. A very typical scene that you might experience with your working in Max for design visualization, V-Ray setup, V-Ray materials. If I go ahead and I open up the material editor and I switch to a different view, you can see this is a pretty standard workflow of what you would be working with in V-Ray. Also, if I were to bring up the end result very quickly, you can see that this is a nice looking render. It takes it probably takes certainly tens of minutes, maybe even a couple of hours to get to this point. But the point being is you get really fantastic results, and that's what we want to help you achieve in the engine. So what I'm going to do is I'm going to pop over to Unreal Engine, and I'm going to show you an example of what a raw import actually looks like. So this file was brought in using the Datasmith importer into the engine. There is a little bit of cleanup here. We just added a reflection. We did add a new floor, and we did do one bake. But other than that, this is what you're seeing on your first pass into the engine. The textures are there, the lights are there, all of the shadow properties from the lights are within there. So we translated all the materials from V-Ray, so those have all come in. And again, it is our goal to get you here. We want to get you to a really nice looking, thank you. Right. And it's all real time. Right? We want to get you here as quickly as possible, and we want you to get you to be able to experience your designs as quickly as possible as well. So interactivity is really important. In fact, let me mention another thing about interactivity real quickly. I'm going to pop over to another scene here, and I want to bring this up. So interactivity obviously is one of the huge advantages you get when you don't have to do a bunch of offline rendering. But we also want to maintain the visual quality that people are used to seeing in the Unreal Engine. So I just want to bring this image up. And this is a good example of where we're able to really shoot for the stars in terms of our quality. On the left-hand side is a photo that was taken of this building as built. And on the right-hand side is the screen grab from the engine as it was visualized in the engine prior to construction. And you can see that our visual fidelity is really, really important to us, and we want to get as close to photoreal as possible. And here's the scene. Here's the scene that was actually in there. In fact, if I want to switch over to a different view, you can see we maintain all the visual quality, we maintain the interactivity in the real time. It's all live for you to see. So that's what we're really shooting for with Datasmith. We want to shave those hours off, and we want to give you the ability to get into the engine and get as close as you can to getting your work finished. All right, so we've taken a look at some design visualization. I want to change subject a little bit and head over to CAD data. And not just any CAD data, but Harley-Davidson CAD data. They make some amazing things, and we want to visualize those things in the engine. I'll say one thing, Harley-Davidson gets it, right? They know that CAD is no longer just cross-sections and dimensions. They know that CAD is no longer meant to just be realized or analyzed. It's meant to be experienced. So the CEO of Harley-Davidson said once, this is not a new generation of riders, it's the next generation of riders. And we want to make sure that the next generation of riders are going to be riding the next generation of motorcycles designed on the next generation of visualization tools. But designing and experiencing CAD does not change the fact that we have an immense amount of CAD data that need to be generated and visualized. In many respects, CAD data in an engine like Unreal Engine is the absolute antithesis of game design, right? A lot of assets in game design are bespoke objects. They're one-offs. They're built for the specific moment in time that that's going to be shown. It's all custom built. CAD visualization or CAD data is not that, right? This CAD data provided by Harley-Davidson is about 2,000 objects. If I recall correctly, it's about 4 million polygons, and they want to see it all. Not only that, it's coming from different sources, right? So they're not designing every part of the motorcycle in one place. This is where Datasmith for CAD comes in. This is our importer into the engine that is designed specifically for CAD workflows. Now, it's really important to know that, like I mentioned, they're making CAD, they're making all these different parts of the motorcycle in different places. So the importer can actually aggregate data from over 20 different sources and bring that into the engine. So that's a huge thing. We want to maintain a very high fidelity to the translation of materials and lights and cameras and metadata and scene structure, just like with Datasmith for 3ds Max. We also are incorporating proven techniques for organization and optimization. We want to fill holes, we want to find small parts. We want you to be able to create repeatable rules that can guide the future work of other projects. So as you have, maybe import one version of the motorcycle, the next version comes in and you can apply those same rules. Now, what this means, this is a new and unique workflow. Before I show you some things on what Harley has created, I just want to mention that this is a workflow that does not require a stop in your favorite 3D modeling and animation package. You can come right into the engine from your CAD design tool of choice. It's a direct from CAD approach. So what I'm going to do is, let me just pop over to another engine here that I have open, and we can see that this is actually the import that we imported directly into the engine itself. I'll go ahead and just rotate around here. Honestly, this is what I expect, right? This is the raw CAD data. All the parts are here, but we really need to get this to the next level as quickly as possible, because obviously that is what the engine is known for. And so why we would want to do that is we want to get to this. And we want you to be able to really make incredible strides in getting your visuals out there. This is what the engine is known for. As you can see, this is a really good looking piece of geometry here. All of the geometry is there. This is the entire CAD model that's brought in here, and I'm flying around this thing really fast. I'm taking my time so that you can take it all in, but you can see it's really high quality, and we're maintaining a lot of our visual fidelity with the original source. So it's all right there. Now the amazing thing about this is this gives us some options. If you're a CAD designer and you're working in the design department, eventually you're going to have to get these things into marketing and sales and previs. You're doing design reviews. You're reusing all of your assets. You're able to reuse your CAD assets in ways that you weren't previously allowed to do it. Maybe you had to stop off in a 3D modeling and animation package, clean it up, do some rendering, and get it out to the real world. In this case, we're stopping right in the engine, and we're able to get you to where you need to be very quickly. So with Datasmith, thank you. Some help with some of our visual team here, so hats off to them. So with Datasmith, we want you to stop focusing on data prep. We want you to stay focused on being creative. There is one more thing I'd like to share. We've shown you CAD to Unreal without needing to stop in some pretty popular DCC packages. But many people still like to have the incredible visual realism of V-Ray imagery. What if there was a pathway to V-Ray that didn't require a stop in something like 3ds Max or Maya? So for more on that, I'd like to introduce Vlado from Chaos Group.
Hello everyone, my name is Vlado. I'm the CTO of Chaos Group and the original developer of the V-Ray renderer. So, for those of you that don't know what V-Ray is, it's a ray tracing engine. It's been around for maybe 15 years now. It's used for a number of things. It's used for architectural visualizations. It's used for product design. It's used for TV shows, commercials, also for visual effects in movies. And actually, if you have been to a movie theater or you watched TV in the last few years, you've seen a ton of V-Ray. Because, you know, those helicarriers and beasts and monsters don't actually exist. So, actually, to recognize that, the Academy of Motion Picture Arts and Sciences recognized V-Ray and awarded it the SciTech Award for introducing ray tracing to the world of visual effects for film. So that was a good year for us. So ray tracing is one of the techniques that so far seems to be best suited for producing photoreal images that you basically cannot tell from reality. It takes a lot of calculations, but it's very accurate. It's based on real-world physics. V-Ray is based on the way lights, materials, cameras work in the real world, so the result is very good. But it takes a while. It's not real-time. We support multi-core CPUs, we support GPUs. We also have distributed rendering, which is a way to take a render and distribute it across multiple machines in a local network, but it still takes a while. So, and Unreal is obviously a real-time render engine, so how do the two go together? We do customers visits regularly, just trying to figure out what our customers need, what challenges they have, and whether we can help solve them. So this past year, the Unreal Engine came up a lot. We have customers that are using it for all kinds of different workflows that are not related to games, really, just all kinds of other stuff. But what was surprising for us is that people actually wanted to have V-Ray inside the Unreal editor itself for a number of reasons. But obviously, if you want to have very accurate reflections or refractions, you need to do this with ray tracing. The Unreal Engine is great, but that stuff is still not possible to get in real time. And V-Ray can do that. Also, if you want to just have a quick look at your scene with full global illumination without having to wait for a baking process, V-Ray can do that for you. And that's why we decided to put V-Ray into the Unreal editor, which is what we have here today. Obviously the data can come in from anywhere. You can use Datasmith or other ways to bring in the geometry, but we also try to make it easy for users that have experience with V-Ray in other products. So we did several blueprints for common V-Ray objects and V-Ray constructs, like the V-Ray dome light. So we have a special blueprint that allows you to basically rotate the HDRI to set the intensity, basically to set up image-based lighting very quickly. And we also have a blueprint for the V-Ray material, which we used for all the objects in this case. And it has the same parameters that you have in other integrations of V-Ray, so it's very easy to pick up and use. But another interesting feature that we added to the from Unreal is there's basically, you can specify a lookup table for converting the real-time materials to V-Ray materials. And in this case, for the red car paint and the black car paint that you're looking at now, we basically told V-Ray to use, for the actual ray traced image, the VRScans material. So VRScans are a way that we developed to scan and render very accurately real-world materials. So basically take a piece of material, scan it, and then you can render it, and it's very accurate. We can also output all kinds of render elements for you, normals, wall positions, diffuse color, and so on. And for this final animation, we actually use the V-Ray light select render element to separate the lighting into different layers and compose them together. So that's my demo. I hope you like it. V-Ray for Unreal will be able to make real time slightly more real. Thank you.
Surprise, V-Ray for the Unreal Engine. Datasmith tools are coming, and we'd like to hear what you have to say about them. You can see a URL on screen. Please, if you're interested in the possibility of joining the beta, register at this link, and when we're ready to share these tools in the very near future, you are going to be the first ones to know. So thanks for this, I appreciate it. I'd like to introduce Martin Crossman at this point from the Twinmotion team, and he's going to show some pretty amazing stuff that was actually constructed on top of the Unreal Engine. Martin?
Hi everyone, I just want to quickly thank Epic Games for giving us the opportunity to be here today to show you our product. So first off, what is Twinmotion? Twinmotion is a 3D real-time visualization software dedicated to architecture. And for our new upcoming release, it's actually tonight, we are launching it for the show. We are really proud to announce that we are using Unreal, which gives our user the most powerful tool for architectural visualization. Here I mean Revit. It's a big project, more than 4 million polygons. The basic idea of Twinmotion is that in one click I can synchronize this project with Twinmotion and begin to visualize it in real time wide away. It didn't go through the cloud, it's local and it's fast. Let's check it out. So here I'm in Twinmotion. Everything you see here, from the PBR materials, the animated people and the cars, has been automatically replaced during this synchronization. We also keep the BIM information, all the data the architect puts inside this project. And we also automatically replace the vegetation. In Revit, we just add some basic billboard with the shape of a tree. During this synchronization, we automatically replace those billboards by Twinmotion trees, which are affected by the weather and the seasons. Talking about that, let's jump into our Nature tab, Weather. So here we have two main sliders. The first one is controlling the cloud coverage. So if I start to drag this one here, cloud will appear, and at some point it will rain. The second slider here is controlling the season. So we start at the summer, going through fall, and now winter is coming. As you can see here, we also have an automatic occluding system that prevents particles from going in, so it will never rain or snow inside the project. There is a lot of features like this one that we had in mind for quite some time, but we weren't able to achieve them with our previous technology. We've been working on Twinmotion for more than 10 years now, and switching to Unreal definitely gives us the power of achieving our vision for the software. At any moment in Twinmotion, we can change the time of day, so we can visualize the project up at noon or at sunset. In Twinmotion, everything is at 100% real time. There is no baking, there is no pre-calculation. It's something really important because at any moment, the architect should have the possibility to change the time, to make sun study, change the weather and the seasons, and see how it will affect the project and its lighting. Talking about the lighting, we just come inside, but right now it's pretty dark. Thanks to Unreal, now we have some GI using the light propagation volume. This was something we couldn't consider before, and Unreal was the only engine on the market that gives us this feature. So here, if I just boost a bit the intensity of my GI, the light is way more entering the building. Another way to show you this GI is just to jump into our material library and drag this orange one here. As you can see, my pillars has been overlaid by orange. Same with this green one here. Another thing that is really important in terms of architecture is at some point to bring life to the project. And what's better way to do so than to add some people? So here, I'm using a simple tool to create a path. Once I release my tool, people will start spawning on my path. When we designed the software, our main goal was to create a simple tool with a really friendly user UI. So it consists of three major panels. The first one on the left is the library that's native of the software, where you will find all the materials, the people, the vehicles, etc. At the bottom of the screen, we have what we call the dock. It's basically where you have all the options and the settings. Like here, my path is still selected, so I can change the type of people, their clothing, the width of my path, or even the density of people. And on the right side of my screen here, we have what we call the SIGGRAPH, where I have all the hierarchy of my project. For this demo, I have already set up a folder with a few more people. Let's just unhide it. So Twinmotion can be used on any project side, from really small individual houses to really large buildings like this one. And at the end, with Twinmotion, we can export 4 different types of media. Image, video and video 360, panorama, and a BeamMotion. The BeamMotion is the standalone exe file. Let's jump into our image and select this first one. So Twinmotion allows the user to do even more, from project review to phasing and variation. In this first example here, we have some leafy tree in front of our building. In the second image here, we have some palm tree. Twinmotion has always been designed to be used at any step of an architectural workflow, from the first sketch to the last render. But now, thanks to Unreal, we are pushing the boundaries of what we can achieve in terms of real-time architectural visualization. And while today Twinmotion is kind of at the end of the line in this architectural workflow, we are also pushing our partnership with Epic Games, so in the future, you will be able to open your Twinmotion file in Unreal and keep working on your project. Thanks, everyone.
I'd like to introduce Greg Schleusner from HOK Architects Worldwide, and Esri Pascal Miller, and Pierre-Felix Breton from Epic Games.
Thanks, Chris. So, like you mentioned, we're going to pick up the scale a little bit to talk about urban planning. So, one of the challenges of urban planning is is generally how you tell a story of something that's gigantic in scale, and you know, in historical times you would have drawn on a wall and tried to get people to figure out what it meant to them. Well, to solve this problem, it's no surprise that we looked to two partners from Esri and CityEngine and the Unreal folks to take our two challenges and put them together. So the typical workflow, we start with imagery, CAD data, GIS information, and you put that together, apply some rules to it, and you generally can generate a city. So here's a good example of one of the scenarios where you use smart codes, and smart codes in this project were just a means of illustrating what kinds of urban districts you'd find based on the color scheme. You put that together with the power of CityEngine and use procedural rules, and you get this very powerful workflow of being able to define many different workflows to generate a city. So from there, I'll pass it off to Pascal, and he'll illustrate how this all comes together.
Thank you, Greg. So here, now you see CityEngine, and the scene which HOK did. And as you can see, this is a pretty huge scene, thousands of buildings, millions of polygons. And with CityEngine, you have all the tools to create the streets and distribute buildings, and yeah, and have different types of buildings, etc. So what you're looking at here is all procedural content, so it means I can go in, change layers of details, or, for example, of course, can edit my building, so I can change the height of the building, or I can change facades or windows. So yeah, so it means you can do all kinds of different architectural styles, and yeah, if you're into procedural content, I really recommend to try it out. There's a free trial. And the coolest thing, next version of CityEngine will have Datasmith export. So that means if you register for the beta, then yeah, you can take in such big data sets with just a few clicks into Unreal. And now I give it to Pierre Felix, who shows you how this looks like.
Thank you, Pascal. So what you're looking at here is the same model that was exported from CityEngine through the Datasmith API in Unreal. We're talking about something like 25,000 plus objects and 100 million polygons that are displaying in real time. The user didn't have much to do with this. It's a simple export, so we carry over all materials, all objects, everything's placed properly. So photoreal information is not the only thing. Through all this, what we are also able to do is, back to those smart code examples that Greg was talking about, is to use Unreal as a presentation tool where we can mix photoreal information and non-photoreal information in such a way that architects can start to use Unreal as a presentation platform where now metadata that gets carried over from CityEngine can get displayed into the same environment, basically. So the other thing that is really interesting is that you know, we can experience city in a real-time fashion. So, for example, in this case, lighting is not pre-baked; everything's real-time, and there's more to it.
So what you're seeing on screen is the perfect reason, exactly the reason you'd want to use a game engine to help tell the story of an urban design project. You can populate a scene with people, help to give stakeholders the ability to really understand how a city works, how they can occupy it, and really feel the context. So with that, I thank you. We're going to pass it over to Mark.
All right, so let me summarize this for you because there was a lot of content right there. So Datasmith, available now in beta. You can go to the website and register. Converting to this Mac scene and virtually lose nothing. Going straight to CAD, tessellation, straight to Unreal, aggregate content. If you want to go push it further to V-Ray. Very cool. Then, you know, an API so that you guys can use our data prep tools, like we worked with Pascal at CityEngine a few weeks ago, sending the Datasmith Open API was able to do the connectivity to CityEngine. And then we have our friend at Twinmotion that are releasing today. So today you can go buy Twinmotion 2018 for the PC and for the Mac, And that is all powered by Unreal Engine, and I hope that's going to help you achieve the role that you want. So, just thank you to my team. 6 months ago, we only had slides and ideas, and we're there at SIGGRAPH demonstrating to you. So, did you like this? Okay. We're almost ready for the double-double, but we have to go through more. And now we're going to talk about real-time production, and to do this presentation, to give you a good idea what we are real-time production, I will call on stage Mr. Brian Poole, our solutions engineer. Brian?
My name is Brian Poole, and I'm Epic Games Solutions Engineer for North America. At Epic, we believe that the future of visual effects and animation production lies in game engine technology. Tools like Unreal are not only capable of producing interactive experiences, they can alter the course of production. And that starts with previs. By using Unreal Engine, storytellers like Halon Entertainment work with directors and supervisors to produce sophisticated previs sequences like those on Planet of the Apes. As a previs supervisor of 17 years, this is why I came to work for Epic. The power of Unreal gives folks like me the ability to tell stories with a level of interactivity that's greater than traditional CG tools alone. Previs has come a long way from just sliding around gray boxes. It's really liberating. So as an extra surprise, we've obtained a short clip from Halon's previs on war. Let's take a look. But it doesn't stop with previs. It's also about taking that data into production and being able to produce beautiful imagery interactively and intuitively. For me, this is truly exciting. But for others, they're just simply blown away. During today's presentations, we're going to break down 3 unique case studies, and you will hear from creative teams about the benefits and the challenges of working in real time. First off, The Human Race, a live-action tour de force highlighting real-time tracking, 360 photography, and 3D graphics, all composited with live-action footage in real time. Secondly, there's Fortnite, and this one's my personal favorite. Here we have a stylized animated short film that models its workflow after classic production techniques. By supplementing traditional 3D tools with Unreal, artists have the opportunity to create content that rivals mainstream studio productions on all levels except one. They don't have to buy a render farm. Finally, we'll take a look at Zafari, an animated children's TV series produced by Digital Dimension. It's going to be airing in October in France, and we'll explore how the adoption of real-time technology has transformed this visual effects studio into a transmedia company. Now I'd like to introduce Michael, Epic Games Director of Cinematography, and Joji, real-time supervisor from the mill, and they'll start the show by revealing the technology used on The Human Race.
Thank you, Brian. Hi, everybody. Thanks for coming. Joji and I are going to talk a little bit about Human Race. Human Race, you may have seen this project that we did for GDC earlier this year. It was a project that was kind of an experiment in real-time workflow. What we wanted to do is try and see how hard it was, how easy it was to use this real-time workflow, and hopefully, work out better for both production and the people, the final viewers. So it was a tight collaboration between Chevrolet, the mill, and Epic Games, and it was pretty cool because basically in its core it was a VFX car commercial. And so what we wanted to try and do with this is work with the mill and try and see what parts of the process we could inject the engine into. So, like with every visual effects shoot, it came with some challenges. Car commercials, however, come with even more challenges, right? So, some of us have been on visual effects shoots. So you have, in this case for cars, you have moving cars, moving cameras. In this case, we have moving cameras on moving cars. We have wireless video. We're beaming video back and forth from the camera card to the BlackBerry. And but one of the biggest challenges a lot of times is it's hard to light and to get right in the shot, and sometimes it's difficult to frame. And the reason is because you're not seeing a live thing that you can shoot against, right? So therefore you're kind of dependent on post-production to see if you got the shot right, or if you have to, worst case, make the shot work, right?
So at the mill, we're constantly faced with these challenges, and to tackle them, we created the Mill Blackbird and the Mill Cyclops. The Blackbird is a fully adjustable car rig that can be used to augment any CG car into any filmed environment. The Mill Cyclops is a proprietary virtual production toolkit that enables us to render, augment, and integrate digital assets into live camera feeds in real time. So on top of the Blackbird, there's a 360 environment capture rig that takes SDI feeds from 4 RED cameras and live stitches them into a single equirectangular feed. This output is wirelessly transmitted to the camera car. And then on the camera car, we have a computer that receives the hero camera feed and tracks the fiducial markers on the Blackbird, creating a pose estimate in real time. This data, along with the transmitted 360 capture, is fed into the Unreal Engine to augment a CG car over the backplate with live lighting from the environment.
So what we have here is just a production still, just so you can get a sense of what was going on during the shoot. So it's pretty cool because we're not only are we doing this live composite that I'll show you in a second, but it was all happening in the camera car. Like you can see down here, the workstation in the lower right-hand corner. That's running the engine and supplying a composite to send back to the director. And so this is actually the feed the director is seeing, like confidence monitor. He's in the passenger seat. And they were static. I mean, they've done stuff with the Blackbird before, but they've never been able to actually see the car being shown live. I mean, it's pretty amazing for them. And that was because we had live video going into the engine to both do the lighting and in the background. So most importantly, we had happy directors. It was also cool because it kind of sped up the editorial process, because we're actually able to capture stuff on the day and then kind of put cuts together pretty quickly. So,
now that we saw how things work on set, let's take a look at a clip from the film.
So actually what we're seeing right now is not a clip. It's all being, every pixel you see is being rendered and composited live in the engine. So if we went through, part of this investigation of this real-time process is to make it customizable, right? So you might want to have the same commercial with a white car, or silver car, yellow car, who likes Bumblebee, right? And also, because all the stuff is happening real time, you can switch the model out of it. So we can go to, this commercial was created to commemorate the 50th anniversary of the Chevy Camaro. So what better way than to be able to swap to the 68 version of the Chevy Camaro. So all these, so all these things are kind of the reasons why we're steering people towards this real-time production workflows, and the benefits are manifold. So we're back out into the engine here, and I'm just going to stop this and play back, switch into simulate. And you can see, sometimes we'll show people that clip and they're like, oh, well, you're probably just switching a bunch of videos, like you got the red video, the yellow video, but we're actually, and I'm sure some of us, people have been accused of that. So actually this is all rendered this is wireframe version of it, right? So we have, we're actually rendering about 10 million polygons here between the two cars, and we're rendering also a shadow casting version of it, because we're doing shadow casting and compositing. So obviously it's playing in real time, but not only are we playing all this geometry, we're also playing all the images that we're using are all EXRs, right? They're full 16-bit half-float, uncompressed EXRs playing back. And we're doing this in 41 milliseconds a frame. When we talk about render times, whoever thought we'd be talking about millisecond rendering times? So it's doing that. We're playing back at 24 frames a second, and it's got, in order to do this, we're basically shoving about 1.8 gigabytes a second
of just footage through the engine and live compositing it.
So we worked with Epic Games to identify and build key compositing features such as layer compositing, color correction, lens distortion, light wrap, and these things allowed us to improve CG renders into seamlessly integrated shots. By shifting our visual effects pipeline into this real-time workflow and using the Unreal Engine, it enabled us to work like never before. So everything from lighting, rendering, effects, compositing, editing, even audio, it all came together in one package. And we were able to iterate easily and really just concentrate on crafting a great film.
Visual effects production, it's all going to be real time, right? I mean, we're much more expectant audiences. They want to see stuff that that's tailored to them. So this has been a fun process, and I think hopefully we're going to do this again. And actually, if you want to see more of this, we're going to be presenting kind of a more of a breakdown of real-time live tomorrow. This is 6 o'clock in Hall K, and we actually have the real Blackbird there, right? So it's pretty cool just to look at just from the tech side. So that and some of the compositing stuff that we demonstrated here is going to be released next week in the Composure plugin for 417. So we're all pretty excited about that. So thank you very much. Next, we're going to bring Andrew Harris to the stage, and he's going to talk about Fortnite and this awesome trailer that we just finished working on. Thank you, everybody.
Thanks, Joji. Thanks, Michael. We're pretty excited to be here today to show you what we've been working on. This year, our mission was to create a compelling and cinematic trailer for our game Fortnite. And we hope that it would look as much like a traditionally animated and produced piece as possible. But it also had to run in real time. For those of you coming from film, 24 frames per second comes down to about 41.67 milliseconds per frame. In addition to showing you this trailer tonight here, we also showed it at the Electronic Theater this year, tonight, and also again on Wednesday night. This is the first time the Electronic Theater has shown real-time pieces. I think we've mentioned it a couple times tonight. We're pretty excited. Those films are being rendered in real time in the show as they play. And that'll be the case here as well. So with that, I want to show you the trailer, and then we'll come back and talk a little bit more about it.
Let's search this dump and get out of here ASAP.
Dump? What's wrong with the dirt?
Yeah, it's everything. Garbage, rats, severe structural damage.
Some people just can't appreciate fine dining. Did you hear that? You got nothing to worry about. Trust me. I've got the heightened senses of a ninja.
Oh, I am so sorry. Hey, it's okay. We're gonna get you out of here.
Oh, thank you. We thought you were more of those things. Monsters are coming.
Looks like we're staying put. Right. All right. You two sit with me.
Yes, ma'am.
Let's get to work. head to the roof for evac.
Aside from the part where we almost died, that was amazing.
Hey, don't mention it. It's all in an eye tomorrow. Alright guys, who's up for pizza? Oh yeah, pizza!
Thanks very much. I just want to reiterate again, that was all rendered in real time, every frame of it, right here on this machine. Michael Clausen, one of the directors of this piece, has the project open right now. So if we go in, we can look in Sequencer, and you can see we split the trailer into 6 sequences. So we basically organized the piece in Engine to be as much like a feature or episodic production as possible. Additionally, we have a new feature in Sequencer that are called priority overrides. And what this allows us to do is set things at a show level. For instance, like prop positions or light position and color at a show or sequence level. And then we can go in and override them at a shot level. This is a paradigm that's very familiar to anyone coming from film or television, where you want to do sort of global work, but then refine it on a shot-by-shot basis. Why don't we jump down, Michael, into the DB sequence. And you can see here are all the shots that are in the DB sequence. If you want to jump down into one of the shots. There are a lot of benefits to keeping things real time. I mean, artists benefit from fast iteration times, and you can easily propagate changes, even if it's late in production. Michael, do you want to pop the camera out and just show how we can rotate around, maybe find a new camera angle? In real time, you can easily explore the fully lit scene and discover new shots, just like you might on a live action set. Lighting is something else that's also totally interactive, of course. And kind of happy accidents can happen. So if you're working in the scene as a lighter, you might rotate a light, discover the way a shadow casts across the set, or discover an unexpected way the light shines on a character's face. Another thing we've been thinking a lot about is how the viewing experience can be personalized for each individual user or audience member. For example, if you're playing Fortnite, for example, throughout the week, you're getting a lot of cool loot. You get some cool stuff. Let's say, how about Michael, like the red ninja outfit? We get a red ninja outfit, and you want to watch the cartoon on the weekend. You can, plug in your PlayStation ID, and now all the characters in the episode are wearing your stuff, the stuff you found in the game. How about the flaming sword? Also, we can do that one. Or how about, I think we've got some white costume and like a laser sword. So it's pretty cool. Another area we've put a lot of thought and effort into is trying to preserve the detailed keyframe performances and high fidelity deformations that we get in Maya. So for this we used Alembic caches. And I'm going to invite Michael Bailout up to the stage to tell you all about that and also the rest of our animation pipeline. So, Michael Bailout.
When we set out to make A Hard Day's Night, our goal from an animation standpoint was to achieve high-fidelity facial performance in real time. I'm going to take you through the animation pipeline steps we used on the trailer to create this level of performance. We started with traditional storyboards to figure out the content of our piece like you would on any traditional production. Once storyboarding was complete, we used our in-game rigs and assets to shoot mocap and brought that into Sequencer to do interactive rough layout. During the rough layout stage, we also did an early facial test with our in-game assets and soon realized we weren't getting the fidelity we were aiming for. Here's that initial facial test created by our animation director, Mark Donnell. With these results, we decided to up-res our models and to help with the deformation, and also separate our heroes into 2 separate meshes, one for the body and one for the head. With our current implementation of FBX, we knew we were limited to the number of skin influences per vertex and limited support of Maya deformers. To resolve this issue, we devised a hybrid Alembic FBX workflow. The result being that we were able to use all the rigging techniques that Maya has to offer. These decisions enabled us to achieve our goal of a high-fidelity, cinematic facial performance. Here's our second facial test using our final cinematic rig, which used joints, blend shapes, and Maya deformers. Once we finished our rig and model updates, we exported our pre-image, which included characters, props, and sets from Unreal into Maya for keyframe animation. Blocking animation was then brought into Unreal as two separate animations to continue to view the trailer in real time. An Alembic cache for the head and an FBX for the body. During the import into Unreal, the Alembic cache was converted to PCA compressed GPU morphs and stored in memory and blended per frame in real time. Body animation was imported as a traditional FBX, and anim dynamics were used to achieve secondary animation details. Once we had approved final animation, we re-imported that animation into Unreal. Using this hybrid approach, we feel we achieved a blend between game and visual effects workflows. And now I'm going to hand things over to Ryan Brooks, who's going to talk about fluid sims and volumetrics. Ryan?
Hey everyone, I'm here today to give you guys an overview of the volumetric storm clouds and fluid sims for the Husbets that were made for this piece. And both of these things were authored and rendered entirely within Unreal Engine. And while both of these, and that includes the real-time Navier-Stokes fluid sim for the Husbets, and while both of these techniques used a very similar ray march material for the rendering, they were authored and animated in pretty different ways. So I'm going to give an overview first of the storm clouds and then of the Husbet simulations. So the storm clouds were a mixture of procedural shapes which were defined as distance fields that could be modulated with noise using the noise node in the material editor. And that allowed us to modify the transform and position each layer of the cloud while looking through the sequencer camera of the cinematic. But you might notice that it still looks a little bit like a typical procedural effect, which is kind of rigid and betrays what it is. So that gets to the next thing, which is how we create a more wispy effect. So look dev with procedural shapes can be a little bit challenging because you have so many different knobs to tweak. There's basically infinite possibilities for how you can make it look. And the team and art director wanted the clouds in this piece to be both billowy and wispy, which you can see they can tend to be a little bit conflicting goals. So what it takes is just a lot of different combinations and experiments of the parameters and sending out and getting feedback and then slowly converging onto the result that you want, which is something close to the bottom right there. And the wispiness there is actually achieved by using flow maps with curl noise, which we could then control per shot. And so for growing the clouds over the life of a shot to create the appearance that they were spreading into the frame and taking over, we were actually able to raise the distance field threshold over the life of each shot, and that allowed them to grow into the noise pattern where the procedural shape was not showing up in the beginning. And the flow maps were what gave the clouds their extra level of detail and animation in addition to the growing across the shot. And I used a technique here which took a few iterations of the velocity texture rather than a single lookup at the location. And that allowed for tracking the more curly, wispy shapes that were desired for this piece. So to create a more whimsical looking piece here, we didn't want something just like the rigid procedural shape on the left. We wanted it to be very flowy and curly and whimsical. And so for some of these shots, that was actually achieved by doing the painting of the velocity in virtual reality with a motion controller. And that allowed for really seeing and defining how those curves would be represented throughout the volume, which can be a little bit difficult to do in 2 dimensions with the mouse. So for the fluid simulations of the husks, it was an idea of one of our effects artists, Bill Klaas, to experiment with some of the fluid simulation techniques I had been doing before GEC, so that we could keep this all inside of the engine. And there were a lot of different reasons that we wanted to try doing that. For one, we had concerns about getting the right rating from the ESRB, and they were concerned about showing too much violence during the husks being shot and spiked to death, basically, in different shots. So we wanted to have a very fine control up to the last minute of exactly how much you saw the husks getting impaled versus turning to smoke right away. And also it allowed us to have control up to the last minute for lighting tweaks as well as just overall look and feel without being locked into re-importing all 25 plus simulations into the engine. And so the characters were able to contribute their density and their velocity into the simulation to create the right effect. So this is just a quick little snip showing a couple of the husk death effects there. And as you can see, when the husks are wiped away, they kind of continue some of the motion that they were doing right before they died. And to do that, we needed to be able to voxelize them, including their motion, into the volume. So this fluid simulation was all controlled through blueprints and materials in the Unreal Engine. And I gave a little bit of a talk on this on GDC, which you guys can probably find online. This is a quick slide from that showing the basic blueprint steps for controlling the fluid simulation. The steps were the advection stage, the divergence calculation stage, the pressure iteration stage, and the gradient subtraction stage. And each steps of those allowed a part of the fluid simulation to be computed using a texture on the GPU. So we didn't have any existing voxelization techniques that would work with meshes, like skeletal meshes with animation. And there wasn't exactly enough time to do the proper development to do that all in code the right way. So I ended up using a fairly basic trick here, which was to take 4 shadow map captures of the character and then multiply those together within the volume. And the 4 cardinal directions were used here because it allowed us to bypass using the full transform and just do squizzles for the math of that. And of course, you can envision scenarios where this might cause artifacts in the voxelization, such as interior cavities that would be missed. But for the purposes of this simulation, it didn't really matter, so this is what we went with. So the simulations were controlled by a combination of different ways. For one, most of them were seeded with curl noise inside of the velocity, which you can see on the lower left there, where just a simple sphere of smoke will dissipate and create nice wispy shapes over time. And the other way that we did that was by using sequencer to control how much each character contributed to the volume. And in addition, on the right there, you can see we added a threshold for velocity to density conversion, so that as the smasher is swinging his arm very quickly, more smoke is emitted from the fastest moving parts of it. And this is a video that I made to kind of demonstrate how the behind the scenes of this was done a little bit, as well as the power of having this kind of simulation in real time. You can actually sit there and scrub in sequencer and get different responses and see the effect of the animation inside of the sim right there. And this actually proved pretty invaluable while trying to finalize the look dev for the fluid sims by being able to just manipulate the sims, change the settings, record little snips, and get feedback from the team and iterate on the look. And in addition, I could actually sit and play with this all day and people would think I was actually working, so it was great. And so people have asked me quite a bit about what are some good references to get into fluids if you haven't done it before, and I usually refer them to the Fast Fluid Dynamics Simulation on the GPU by Mark Harris, which is on GPU Gems, because it was a great thing to introduce me into it, as well as a couple other little volumetric talks that I think are useful as well. And then I've written about some of this in my blog as well at the end there. So that wraps it up for my part of the demo, and I'm going to hand things back off to Brian Poole, who's going to summarize the Fortnite section.
Thanks, Ryan. Wow, I feel 10 times smarter. How about you? All right, so far we've seen 2 of our 3 presentations, and before we get to our third, I'd like to add that Epic's growing enterprise team is designed to help you deploy these types of pipelines into your specific workflows. Please feel free to approach any of our presenters after the show. Now I'd like to hand off the presentation back to Mark T, who will introduce you to the world of Zafari.
Alright, we are almost there. This is the one more thing moment. And I'm very proud of this last presentation. You know, the cinematics team at Epic Games has done an amazing job. You've seen the results. It's fantastic with the help of the mill. But now we have we're going to call on stage our friend from Digital Dimension to talk to us about Zafari. Gentlemen, please come with me. So please welcome David Gozoratz. He's the director and the creator of Zafari. This is also the deputy producer, Pierre Bezo, the CTO, and we see moment now the president of CEO Digital Dimension. David.
Hi there. My name is David Gozoratz. I'm the creator and director of a kids animated television show called Zafari. And the show is about animals that are magically and mysteriously born with the skin of other animals. Our goal for the show is to not just entertain, but to actually help teach kids that that which makes us unique, that which makes us different, is not only something that should be tolerated, it should be celebrated. So this notion that being different and doing things differently is a good thing. It's something that permeates everything that we do at Zafari. And when Digital Dimension came to me and suggested that they abandon 2 decades worth of traditional software pipeline rendering, and they wanted to do the rendering for the show in the Unreal Engine, I was excited and skeptical, excited and skeptical, because we were talking now about broadcast quality, 9 hours for the whole first season, broadcast quality animation. So could we do it at the level in a real game engine that we needed to do it in? Let's see.
Wow. Really game engine, ladies and gentlemen. So David, what did it mean for the creative process to use a game engine?
Well, I gave Digital Dimension a pretty high bar to be able to jump over because we did an initial test for the broadcasters in a traditional, very highly regarded CPU software renderer, and it had subsurface scattering, global illumination, ambient occlusion, vector-based motion blur, all the things that I said to these guys, the game engine would have to be able to jump over that bar in order to do it. And it did it, and we've got, so far, 2.5 hours in the can, quickly on our way to 9 hours for the first season.
Amazing. Peter, you're the exec producer, you're responsible for budgets.
Yeah.
How did it go?
Well, as you saw, the ambitions that David set for us were extremely ambitious. They were high. And as a producer, you're always sort of looking to, on the one hand, control your costs, and on the other hand, elevate the quality of the project. We've been toying with Unreal for a couple of years, but this is the first project where we thought, you know what, this would be the right project in which to actually test it out and see if we could actually make a go of it. And we've been doing it now for about a year. As David says, we've got about 2.5 hours of material that's been output. We have 10,000 shots that we're going to have to output by the time it's done, so we really need to make sure that we got it right. And so basically from a cost and a quality point of view, I can speak to that very briefly. From a cost point of view, in terms of the material cost, it takes normally 3, 4, 5 different types of software to light, render, do effects, comp your shots, update your shots. Here we're doing it all in Unreal. We're rendering on one computer in a corner somewhere, which means that the whole render farm and all that, we're completely bypassing that and all of the costs associated with having a big massive render farm out the window. In terms of human cost, well, the fact that we can iterate, we can render so quickly means that we've been able to reduce the time that it takes for us to light, render, composite, upload our shots as compared to our original estimate with our original pipeline by about 75%. So that's like a 300% increase in productivity. So we're obviously very happy about that. So in cost-wise, that was really cool. Then you have to look at obviously the quality. And in terms of quality, well, one of the things that the technology allows us to do, and you saw it there, was to build really big sets, really deep sets, lots of vegetation. It's all CG, there's no matte painting. There's simulation, the leaves, the whole kit and caboodle. David was very insistent on that, and thank you for challenging us. And so we're able, yeah, I know, it's season 2. So we're able to do that. And when you take all those different elements combined, and you give this to the lighters, and the lighters basically can light and get instant feedback on the work that they're doing, they can iterate to their heart's content. So we're looking at 5, 10, 15, 20 iterations of lighting before the lighter even submits a shot to lighting. Now what this does is it allows the lighters, or allows us as project managers, to hand over entire sequences to the lighters. One lighter lighting an entire sequence is lighting in continuity. You all know where that goes. And then when we hand over the lighting to David for feedback, we're handing over an entire episode of 11 minutes that's been rendered on that one computer in about 3 to 4 hours. So overnight, he sees the entire episode lit. And so the feedback he gives us is feedback that is given within the context of that continuity. So if you look at it as a producer from a cost-benefit standpoint, costs go down, quality goes up relative to what we were expecting. I can't be happier personally.
Wow, sounds like you can have your cake and eat it.
Yeah, for once, yeah.
Okay, talk to us about the pipeline quickly.
Well, for the pipeline, we are a small studio, so we have limited amount of engineering resource to integrate like traditional animation pipeline with Unreal. And on the other hand, we have limited resources as like experts in Unreal. So it led us to a pretty conservative approach. So in the end, we have like shotgun automated events that would bake all the data and export contents in FBX. Then in the middle, we have this like perforce version file of FBX and Unreal ready assets. And then you have like an automated / manual process to ingest all the data and reform the sequences in the sequencer of Unreal. And then from that, we would render shape the whole pipeline to output the images for review. So it would take us like less than 3 hours per.
He has a laptop and he has 12 minutes of Zafari running in real time. So his 1 frames per second thing, that's history.
Yeah.
He can show you, so track him down with his laptop and he'll show you Zafari running in real time in Unreal Engine. So, Pierre does it for you. So, Louis Simon.
Well, the future is exciting for us. We're thrilled. This is a fantastic project. Digital Dimensions, for the ones that don't know us, we came from here. We were born in Burbank, and the studio grew over the last 20 years plus from a visual effects studio, and then we evolved, we pivoted to 3D animation, and through the use of this new technology and these projects, it got us to thinking we can actually get much bigger than this, and we are set to literally transforming ourselves yet again into a fully interactive, integrated, should I say, transmedia company, which will encompass for studios. So this is much, much bigger than we've ever done, and it's thanks to these technologies. This gets me to think, you know, your guys were mentioning before about all the efficiencies that we managed to get through the pipeline. And I'm reminded of this old adage that we all know here, whether you're on the client side or you remember cheap, good, or fast, pick 2. Everybody remembers that? Well, for the first time with these projects, and David can attest to this, we feel we can finally bridge the gap in between those three critical elements that are beneficial and necessary for the development of a long-standing, strong franchise. So before we end, I want to tell you how proud I am of our respective teams at Epic and Digital Dimension. These guys have been working, and the people down in Montreal, tirelessly for a long, long time, and it's paying off, and we're very, very proud. Thank you to our partners. Thank you to Intel, Asus, NVIDIA, Microsoft, Corsair, and the many others that are so generously helping us throughout this project. And lastly, I want to thank you, Mark and Tim, and everybody here at Epic. You guys you've been great partners. You've been open and very straightforward and engaging with us ever since the beginning of this great adventure. It's only just the beginning. Thank you for this opportunity to be able to share this moment with our peers, and we look forward to a long and fruitful relationship with you.
Thank you guys, this is amazing, this is the future. So, David, good luck with the project. Thank you so much. Thanks guys, we are almost done, thank you. So, to close, I really want to thank everybody. I think you understand why I'm excited now and why the excitement is building around the Unreal Engine and all of the things that we can do for you and build for you. So please, all the speakers, the enterprise team are all going to be out there. They will be